Another force to add to our list of forces is the elastic or spring force. Here I have a mass sitting on a frictionless horizontal surface. One end of a spring is attached to the mass. The other end of the spring is attached to a wall. This gives me a horizontal spring and mass system. When the system comes to rest, the mass will be at equilibrium, denoted here by x0. Equilibrium is the point where the net force acting on the mass is zero. For a horizontal spring and mass system, the equilibrium point is the point where the spring is not stretched or compressed. As I begin to pull the mass away from equilibrium, the spring will begin to exert a force on the mass that pulls it back towards equilibrium. So if I pull the mass to the right, there will be a spring force pulling the box back to the left. As I pull the mass farther away from equilibrium, the spring force grows larger. In the first picture, when I had pulled the mass a distance delta L1 away from equilibrium, the magnitude of the spring force is still relatively small because the distance delta L1 is not very large. When the mass has been pulled a farther distance, delta L2, away from equilibrium, the elastic force has grown significantly larger. The farther the mass gets away from equilibrium, the larger the force will be that is exerted on the mass by the spring. We can express the relation between the magnitude of the spring force and the distance the mass has been pushed or pulled away from equilibrium. The magnitude of the force exerted on the mass by the spring is directly proportional to the distance the spring has been stretched or compressed. The constant of proportionality in this case is the spring constant of the spring. The spring constant K is a measure of the stiffness of the spring. The stiffer the spring is, the harder it is to stretch or compress, and the larger the value of the spring constant. Notice that in this equation, delta L has been defined as a distance, not a displacement. As a result, delta L is always a positive quantity, regardless of whether I stretch or compress the spring. So what happens if instead of stretching the spring by pulling the mass to the right, I compress the spring by pushing the mass to the left? The magnitude of the spring force is still proportional to the distance I have pushed the mass away from equilibrium, but the direction of the spring force is flipped. As I compress the spring by pushing the mass to the left, the spring now exerts a force on the mass that points back to the right. Therefore, the spring force always pushes or pulls the mass back towards equilibrium. As a result, the spring force is known as a restoring force. The spring force is always trying to restore the mass back to its equilibrium point. Because the spring force is a restoring force, the vector equation for the spring force can be written as F sub s equals negative kx. K is still the spring constant, but the x in this equation is defined to be a displacement from equilibrium. Unlike delta L in the equation for the magnitude of the spring force, x is a vector and does care about the direction the spring is stretched or compressed. The minus sign in the equation tells us that the force exerted by the spring always points in the opposite direction as the mass's displacement from equilibrium. If the mass has been displaced to the left of equilibrium, the spring force will push on the mass back towards the right. If the mass has been displaced to the right of equilibrium, the spring force will pull the mass back towards the left. Our vector equation tells us two important things about the spring force. It is a restoring force because the force always points in the opposite direction as the displacement of the mass. It is also a variable force because the strength of the force depends on the position of the mass relative to equilibrium. As the mass moves around, the strength of the force exerted on it by the spring changes. The more you stretch or compress the spring, the larger the magnitude of the spring force gets. Because the spring force isn't constant as the mass moves around, we will tend to focus on spring force as a force only in situations where the mass doesn't move. These problems are known as static equilibrium problems, so the net force acting on the mass must be zero.